same? It's okay. Is it okay? Okay, we are going to resume Compton scattering, in which we are now treating, so we started with light as an electromagnetic wave. Now, that's the prescription that we are not using anymore when we deal with Compton scattering, because what we are doing now is to define light as an ensemble of photons, a stream of photons. And in this way of thinking, if we had a free electron, we had an incoming electromagnetic wave, which is carrying an electric field which is oscillating. Because of this oscillation, the electron is going to move up and down, acceleration, and therefore the incoming electromagnetic field is creating this acceleration in the photons, Larmor formula, emission of photons in some other direction. Through that, we basically computed the Thomson cross-section, which tells you what is the fraction of flux in terms of a fictitious area that a free electron has when an incoming electromagnetic field is basically shining upon to it. Then we have also seen the case in which we have a bound state in which the electron is orbiting around an ion, and we've seen that the cross-section is different for the same kind of particle, which is an electron, but the system is different. So you see the overall system is this one, and the electron is going to behave to scatter. The scattering process is going to be different. The cross-section is going to be different. And it has a different angular dependency, a different frequency dependency, as we have seen. Now with using this other prescription, light with like a stream of photons, we are considering the situation in which we have an electron, we have a photon that is basically going to interact with the free electron. The electron, in general, can have its own for momentum, energy and momentum. The same is true for the photon. After the interaction occurs, the electron can change its course of direction, its motion, because there is an energy momentum exchange, as well as the photon can also change its direction of propagation and frequency as well, because he's participating to the energy momentum exchange, which overall has to be conserved. Therefore, we are going to have a photon which is going to have a different frequency, and as well as the form momentum for the electron is going to be different from the one of the initial state. And in general, this is a reaction in which we have a photon plus an electron. This depends on the fact that there is a reaction, therefore an interaction between the two that is going in this direction only. And we are going to have another photon and another electron, but with a different energy density, because as I said, what is conserved is the total form momentum of the system. So we have the electron, then we have the form momentum of the photon that must be equal at the situation after the interaction, which is with the prime indices in which the energy momentum exchange took place. Then we just plugged into these 4 equations, because mu ranges from 0 to 3. We solved this system of equations, and in the end, we looked for the change, the percentage change in the frequency of the photon, averaged overall angles, which is equal to, the final result was 2 pi, pi classical radius of the electron over sigma Thomson, ln 1 plus 2 epsilon squared plus 2 epsilon plus 1 minus 2 epsilon 1 plus epsilon all over 3 over epsilon to the power of 3 minus 1. So you see that the Thomson cross-section appears in this Compton scattering, but the interpretation now is different because before we were thinking at the cross-section, the Thomson cross-section has the capability of the electron to capture an incoming electromagnetic wave. Now, the overall cross-section that is governing this interaction and this that in the end enters into percentage change in the frequency of the photon after the interaction has to be thought as the probability to interaction to occur. Okay? Therefore, when you speak about the cross-section of interaction between particles, is the probability is always expressed in terms of an area, but it's because then it's always related to an energy exchange. But per unit of time, per unit of area, therefore usually you always express in terms of area, but it has to be, it's related to the probability of the interaction to occur. So you see, it's a different way of thinking, it's a different kind of meaning. Now what we do, you see this kind of a little bit weird equation, not that explicit. So what we are going to do now is to make an approximation. And we are going to consider epsilon, that I remind you is the energy of the photon, is the ratio between the energy of the photon over the energy of the electron. We want it to be much smaller than 1. So we have a low energetic radiation, low energy photons, with respect to the energy of the electrons. That's very relevant, for example, in the cosmic microwave background, and the interaction of the photons of the CMB, the cosmic microwave background, with the free electrons that are in galaxy clusters, as I'm going to show you. Okay? Now, what we do, we basically expand this logarithm up to the term in which we have the argument here, the 2 epsilon at the power of 3, because then there are cancellations that are going on into this equation. And what we get is the epsilon over epsilon is 8 pi r e squared over 3. So you see here is the third term in the Taylor expansion of the logarithm. That's where this 3 is coming from. 1 minus epsilon. And then we have the minus 1. Now, if we isolate all these terms, we basically see that that's equal to the Thomson cross-section. And here we get a 1. Sigma Thomson over sigma Thomson is equal to 1. We are left with this equation, for which we basically have minus epsilon. Now, if I plug in the definition, right, this was the definition, h bar omega over m0 c squared, if we put ourselves in the rest frame of the electron. So what you see, these are all positive numbers. There is a minus here. What does it mean? That the frequency of the photon after the interaction is going to be lower with respect to the initial frequency of the photon. Okay? The photon is losing energy. For this scenario, not in general. Okay? Keep this in mind. And that's an approximated result. But where is this energy gone? It went to the electron. The energy went to the electron. So the gain in energy from the electron is plus this number. Is a transfer of energy. Good. Now what we want to do is to look what is the total energy exchange between the photon and more electrons, because this is only one scattering event. Now what we want to do is to look what happened in a more useful case for astrophysics, in which we do not have an isolated electron incoming photon, but we are looking what is the interaction of this photon with more electrons, because imagine a plasma, we have our ions, we have our electrons, and then we are going to have the interaction between these charged particles. So this kind of interaction also occurs on with the ions, but as we have seen in the previous lecture, the cross-section of ions is way smaller with respect to the one of photons. Therefore, the probability of such an interaction to occur with respect to the one with the free electrons is way lower. So whenever you have a plasma with charged particles, the ions, and the free electrons, what is relevant in the end are the interaction of the photons with the electrons only. You can neglect the photons because, as we have seen, the cross-section of, the one of the ions, because the cross-section of ions is way smaller with respect to the one of photons, the one of electrons, okay? So let's do that. Now, interaction with more photons, with more electrons. And what we want to do is also to change the prescription with respect to energy, because we are speaking about frequencies, but what we want to do is also to relate to the power of the emission of the radiation. Therefore, we are going to go into the regime of frequency, of energies. So what I'm doing here is just bringing the omega on the other side. So we have minus h bar omega squared over m of the electron c squared, that I can relate to an energy. I just have to multiply this term by h bar. Right? We have seen in the last lecture that the energy of a photon is h bar times the frequency omega. Therefore, the change in the frequency, in energy of our electron is exactly that number, but where we are basically including another h bar that goes to a square here. Again, this is still one electron. You see, where is the number of ions? Is not there yet. Now, when we want to use more ions, we just are going to have that number scaled for the number of interaction that we have per units of second, given a certain number of ions. Does it mean that the change in energy per unit of time is going to be equal to minus, that is coming from there, because it's a loss of energy, c, which is the velocity of the photons, the number of electrons, twice the number of electrons, the number density of electrons, twice is going to be the probability to interact, of course, and then the cross-section, which is the probability for the interaction to occur. See, it is a flux. And then we have our h bar square omega square me c square, which is the energy of each individual interaction. This is also called collision rate. And if you look at the units, we have meters per second, that's the velocity. We have a number density, which is 1, because number don't carry any units. Density, therefore we have meter cubed. And then we have a cross-section, meter squared, m squared over m to the power of 3, cancel out. The units are 1/second. You see energy per unit of second. Energy per unit of second. Okay? You can also see it in a different way. If we bring the dt on this side, we have a velocity, we have a number density, then we have velocity times a time, which is a thickness, times the area, that gives you a volume. Number density times a volume is a number, so it's the number of interactions. Okay? Good. And that's it. So you see that with the Compton, with this prescription, there is actually this energy transfer to the photons, or if you wish, the energy gain of the electrons that is coming naturally in this prescription, whereas in electrodynamics this was not foreseen. Good. So that's what's happening to the photons. Let's see now what is the loss of the photon that is going to the electron. But we know that the electron from the previous lecture is going to radiate as well because of the Larmor formula. And we can look what is the gain of the photons. Gain of the photons. This is the loss, and this is the gain. And that's going to be equal to the opposite of what we have seen when we did a back reaction after we completed electrodynamics. So we know that from back reaction, so I'm using one of the results that we already did, we know that the power of the electron net that takes into account the power that is emitted by the electron minus the power which is absorbed is 4/3 beta square gamma square C U sigma T. That's what we have seen. Now, what we care about is to look, you see, we now need to relate this energy density of our field, which was coming from our understanding of light as an electromagnetic field. We have to relate it to particles. Therefore, we have that U is equal to U omega, the omega. This is still something related to the particle, to the electromagnetic field, because we are always speaking about energy density of an electromagnetic field, of an electromagnetic wave, but per unit of omega. Because I want to look what's happening to the photons that have that frequency. Okay, so it's spectral, it's the spectral distribution. Better to say that's the energy density, and this is the spectral distribution. So how can we make then the jump from here to a prescription that is based on photons? Well, let's keep all the constants that are taking place. So we have 2/3 beta square gamma squared, C. Nobody touches them. Sigma Thomson will remain the sigma Thomson. What we do is to work out on this term, which is going to be related directly proportional to what? The number density of photons that have the frequency omega time the energy of those photons. So So you see, it's a number density, so it's a number density of photons multiplied by the energy of those photons. That's the energy density that are carried by the photons, which is an energy density carried by an electromagnetic wave with this frequency. You see, I just broke this term into particles, and each of these particles is carrying its own contribution of energy, and the overall is, of course, related to the number density of those particles. And then we have the Thomson cross-section, which is left there. And as we have seen, these are all positive numbers. Therefore, this is the energy that the electron is giving back to the photons. Good. Now let's go and join all of this together, because we have the d over the t, which is the power of the photons, of the energy lost by the photon. We have the power that the electron is going back to the radiation field. But remember that this thing here was for all photons, you see, but only one electron. So what we need to do now is to look what is the energy which is given by one of these interaction for each individual photon. For P gamma, I call it plus because it's a gain, which is that guy up there, because the energy that is lost by the electron is the one that is gained by the photon. That's related to all the photons, because you see there is a n gamma. I want to know what is the gain given by one photon. Therefore, I just divide by the number of photons that have that frequency. But as I said, there are more interactions taking place, because already there I'm taking the interaction of one photon with many electrons. Yes. Therefore, I just multiply this term by the number of electrons that are going to have their own energy, which is related to how the electron is moving, beta. Now I just plug in our result from there. The n gamma cancels with that n gamma. And what we are left with is the number density of electrons, for term, which is a constant coming from there, beta squared, gamma squared, beta, c, h bar, omega, sigma Thomson. But yet, these are not all. These are not all photons. This is not what is happening to all electrons. These are, as I said, the electrons with this beta. So what we need to do now is to integrate overall beta, so that we have the overall power that is given to the photons for all the electrons with all the beta. This is one photon, let's be clear, for all electron with a certain beta. So now we integrate over beta. So we do that. P gamma plus, and I call it total, because it's our final result now for this bit of computations. I have all the constants for third, c, h bar, omega, constants with respect to beta, because the integral is only with respect to beta. So I'm carrying out from the integral all the terms that are not functions of beta. So we have our sigma Thomson, and then I integrate between 0 and infinite of NE beta, beta squared, gamma squared. That gamma, remember, is a function of beta. In the beta. Now what I can observe, I can see that if I take this function here, the integral this integral here, you see, this is actually the total number of electrons. And E is equal to the integral between 0 and infinite of NE beta, the beta, right? I have a number density, number of electrons as a function of beta. I integrate over all beta. I get all number density of electron. Okay? So you see I have a distribution that is normalized in this way times a function which is this one. So I can relate this quantity to the average of this function, which is beta squared gamma squared. So all the constants are left. Oop. And then I have the average of beta squared gamma squared beta, but it has to be normalized over NE, because the function that is weighting the distribution, which is this NE, which is weighting the function integral, must be normalized to 1. And the normalization is taken care by this factor. That's something that we already done in the past lectures for other quantities. Oh, sorry, this is NE goes here. And that's obvious, because if I increase the number of electrons, the total power, I have more scattering events, and therefore the total power must be larger. Okay, yeah, because this guy is the average, which is normalized over NE, but this NE is not appearing here, so I have to multiply by it to cancel it out. Okay, now that I have everything, because this is now the total of the energy exchange with the electron for all the, so of the photons for all the electron, I just look at the final results. So the net energy transfer to the E minus, sorry, to the photons, the E gamma over the T, that's the total one, is going to be equal to the one that is gained by the photons, gamma tot, plus what is left, as what is lost by the photons, P minus gamma, which is the function up there, where I wrote loss. I plug into here and into here our results, and what we get is C and E sigma Thompson H bar omega for third average of beta squared gamma beta beta minus H bar omega ME C squared. I'm not using a laser because on the video it wouldn't be invisible, so I'm trying to use this low-tech stuff. I hope it works. Good. So that's basically all about it. you see that we change the prescription of light from an electromagnetic wave to the fact that we are actually particles interacting one with each other. We have photons, not anymore electromagnetic waves. And we discuss the interaction between one single electron with one single photons. We have an energy momentum exchange, where the total energy momentum of the system is conserved, is a conserved quantity as we have seen. By combining those four equations that involves the four momentum of these two particles, we derive the change in the frequency of the photon after the interaction. Then we used an approximation, and we just consider the case for which the energy of the photons is way smaller with respect to the one of the free electrons. That gives us this result. So that's the approximation that we are using, where we see that we have a loss of energy carried out by the photons. So the photons are losing energy. Their frequency in this bit of computation is getting lower. Then we consider the fact that we don't have the scattering. If we are considering a plasma, we don't have the scattering only with one individual electron, but we have many electrons. And as I said, only the electrons are relevant in a plasma because the cross-section of ions is way smaller with respect to the one on electrons, and they can be safely neglected. And gave us the total loss of the energy for our photon, where the link between frequency and energy is given by the fact that the energy of a photon is just h bar omega, the frequency of the photon. So this is the relation between the two. Then what we did was to look this is the loss. Let's see what is the gain, because we know that the electrons, when we studied back reaction, we have seen that the electrons are giving some energy back to the photon, to the radiation field, which is this one. Now what we did, we related the energy density of an electromagnetic wave from our prescription coming from back reaction to a particle interpretation of it as a number density of photons that are carrying a certain energy, h bar omega. This is the energy of one photon. You multiply by their number density, and you get the energy density of your collection of particles, of the light interpreted in terms of photons. Then what we did, we look for, this is for all photons, because this is referring to the radiation. Electromagnetic wave is the full radiation. Therefore, it carries the contribution from all photons. So what we did now was to look what is the gain for one photon only. That's why we divided by n gamma. And then we multiply by n the number density of electrons, because we wanted to see the interaction of this electron, this one photon, sorry, with all electrons. And that's what we got. Then this is for with electrons which have a specific velocity, a specific beta, which is related to gamma as well. And we integrated overall possible beta, arriving at that. So we have the loss, which is up there. We have the gain, which is down here, of the energy per unit of time that is acquired by a photon. And then we look for the net energy transfer. So the net energy that is going to experience our photon, which is just the sum of the two, where this guy here is negative. So we have the gain, and then we have this guy, which is negative. They give us this final result. Now let's see an application to astrophysics, in which, for example, the photons are given the number density of photons is related to, so the number density of photons, which is related basically, which basically gives you a spectrum. So that's omega, and that's your spectrum. So that's the energy distribution as a function of frequency. And let's take, for example, the Planck spectrum. that I'm going to derive in the next lecture. But I want to anticipate it now here, because you all know what the Planck spectrum here is: the spectrum of a radiation field in equilibrium. So the photons are in equilibrium. The radiation of a black body. What happens to this spectrum if they are going to interact with a bubble of plasma? Let's say we have radiation coming from this direction. Let's say that we have a bubble of plasma. Okay, so it's like a cloud, better to say, of plasma, with the ions and with the electrons. And as I said, the electrons are the ones that are relevant. We are going to have Compton scattering. And let's assume that the incoming radiation has an energy, h bar omega, which is way smaller than the one of the electron. Okay, that's the assumption. So what's happening? It's going to happen that we are going to have a change in the spectral distribution of these photons. And if this is the case, the spectrum, the spectral radiation, so each frequency is going to experience this is going to experience a gain in energy. Because we have the loss, we have the gain, but in this approximation, the gain, you see there is a minus, but as we said, this quantity here is way smaller with respect to 1, therefore we have a positive number. So we have a gain in this approximation. What's happening to the overall spectrum is it is kind of moved toward higher frequencies. Higher frequency means higher energy. And the spectrum is going to look something. There is a distortion, okay. Overall, it's kind of Planck-like because the overall spectrum is not changed much. It changes a bit. The shape is not a Planckian spectrum. So if you now measure the distribution, if you take the spectrum of the radiation here or here, you see that it's going to be different. And what is funny here is that if you are observing at this specific frequency, you see, they have exactly the same amplitude. It looks like that they have exactly the same temperature in terms of radiation. If you're observing in this frequency, you see that the temperature that you would measure for the photons here is lower with respect to the one of the unperturbed incoming spectrum. Therefore, you have that the temperature of your photons is smaller with respect to the incoming radiation. If you look on the other side of the spectrum, here, you basically see that the photons are kind of hotter. You have more photons with this higher frequency. Where is this happening in our case? When do we have this situation? We have that with the cosmic microwave background. That I'm going to discuss after I completed the discussion with the Planck spectrum. We have a galaxy cluster. And that's what we're going to see in the cosmic microwave background. Imagine you have your millimetric observatory, like Planck, for instance, is a satellite that maps the entire sky. You're looking into a certain direction. You see the photons of the cosmic microwave background, almost uniform with the same temperature across the whole sky, with some intrinsic fluctuation, which is given by the intrinsic matter fluctuation, energy density fluctuation, better to say, of the plasma that emitted that radiation at that time of the cosmic history. You are observing this direction. We have a galaxy cluster here. So if we are observing at this frequency, we completely don't see the cluster because the temperature of the photons that I measure for the different parts in the CMB are not affected at all by the galaxy cluster. If I'm observing at lower frequencies, then I'm going to see a cold spot. If I'm observing at higher frequency, then I observe a hot spot. So that's how people detect galaxy clusters in the millimeter wavelength. They observe the CMB, they do it at different frequencies, and then if they have a region in which at one frequency there is a cold spot, nothing, and a hot spot, there is a galaxy cluster there, because Compton scattering with that approximation is taking place. And then once you have that, you can use, for example, the number of galaxy clusters that you have as a function of mass at a certain redshift, or at a certain distance with respect to yourself. This is called mass function, which is tightly related to the overall properties of the universe. And it's going to tell you what is the amount of matter that you have across the universe, what is the amount of dark matter that you have across the universe, what is the amount of dark energy that you have in the universe. Okay, so it's going to give you cosmological information. But I leave this to the cosmology lectures. Okay? Just here I want to show you the link between the astrophysics that we are doing and also other applications, such as these cosmological applications. Okay? Good. Okay, we can have a break here, 15 minutes. So I see you 15 minutes at 10:15.